All right, everybody, let's go over some questions from unit 1. All right, question number 1. Select delta E versus temperature graph corresponding to transition H to G. So H to G is this transition over here. You're going from, okay, this is our, let me say, okay. So we have our solid here, liquid here, and the gas here. So we are going from gas to solid in transition H to G. And then if that is the case, okay, and also you can see that you're going from a higher temperature to lower temperature. That means you're cooling in this case. Okay, so it's a cooling process. Now let me draw this. This is 0, this is delta E, and this is temperature. So we are starting at a higher temperature. That means delta E must be 0 at a higher temperature. Okay, delta E 0 tells us where we start the process. Always at the starting point, we haven't changed the system, therefore delta is 0. And then when we cool it down, when you decrease the temperature, delta E decreases. And then at the phase transition, that is this boundary, when it crosses the boundary over here, there should be a change in energy, but not a change in temperature. So this must be our freezing point or freezing temperature. Then once everything is converted to solid, then again, when you decrease the temperature, the energy changes like that. So it should look something like this. So every time when you get a question like this, I suggest that you generate your answer like I did over here and see what matches with your answer. And you can see that what matches with our answer is option B. So I'm going to select option B. Okay, so as my answer. Okay, so it cannot be, we are cooling, so delta E needs to go down. And then C cannot be the answer because we are starting at a lower temperature and going to a higher temperature. That is wrong because it's to G, high temperature to lower temperature, right? Because remember, always we read this graph from always delta E 0. Okay, that's our starting point because at that point we haven't done anything. And then it cannot be D, okay? It needs to be negative. Delta E must be negative. And then D and E are not possible as well because it doesn't show the phase transition, something like that. All right, so the correct answer is option B. Let's select that. And moving on. According to the data, which species are in the liquid phase at 30 kilopascals pressure and 310 Kelvin? Okay, so what we need to do is mark these conditions, 30 kilopascals and 310 Kelvin in our graph. Okay, so 310 Kelvin is over here, 30 kilopascals is over here. Okay, therefore they meet this point over here. Okay, the question is, which species are in the liquid phase at this under these conditions? So just to remind us, these are vapor pressure curves. Okay, and if you can remember the phase diagrams, and these are the boundaries: solid gas, solid liquid, and then liquid gas boundary. This is pressure, this is temperature. Okay, and then the idea is this liquid gas boundary is what is plotted as the vapor pressure curves. Okay, and we know what we have is a solid, this is liquid, and this is gas. So above the curve, if you're above the curve, like if you're here, you're a liquid. If you're below the curve, you're a gas. That's the idea. Now, according to this, this dot on the blue dot is below the curve of ethane. Therefore, ethane must be in the gas phase, but it is above the curves of acetonitrile and butanol. Therefore, with respect to butanol and acetonitrile, it must be a liquid. So the correct answer is acetonitrile and butanol, and that is option B. Okay, let's select that. Moving on. Question 3, different substances have different melting points because they are particles. Now here's the thing. The differences in melting temperature, boiling temperature, density, viscosity, and so forth are due to the differences in intermolecular force strength, or differences in attractive interactions between the particles. That is it, not the weights. So option A is out. I'm moving with different average speeds. No, that's not the reason. Are located at different average distances. That is not the reason. Interact with forces of different strength, and that is correct. All right, moving on to question 4. Let's take a picture of this. Given the data provided, select the temperature range for which a mixture of these 4 substances would have to be represented as shown below. Okay, now what we are seeing here is we have nitrogen in the gas phase and also hydrogen in the gas phase. Everything else is in the liquid phase. So the idea is, with respect to the boiling temperatures of hydrogen and nitrogen, okay, so hydrogen and nitrogen, okay, the temperature must be above the boiling temperatures of these. Okay, so let's see. So the hydrogen and nitrogen has 21 and 77, so it needs to be above that. It needs to be above 77. This should be our cutoff. Okay, should be above 77, and then both CH4 and HCN are in the liquid phase, meaning the temperature is below the boiling temperature of CH4 and HCN. Therefore, the temperature must be between 77 and 112. This should be the region. We should be somewhere around here. Anyway, so that answer is actually here. Yeah, this is our correct answer. Okay, option D. Okay, let's select option D. Moving on. Okay. The wave pressure curves from methanol, water, and acetone shown below. Use the data to rank the strength of interactions amongst the particles of methanol, water, and isopropanol. Okay, so the idea is stronger the attractive interactions, so stronger the intermolecular forces, lower the vapor pressure. Okay, so everything else like melting temperature, boiling temperature, density, viscosity, and so forth will be higher if you have strong intermolecular forces, but something like vapor pressure and the volatility must be lower with stronger intermolecular forces. Okay, now water in this case, which is the green, the orange curve, should have the strongest intermolecular forces, because you can see that at any given temperature, let's pick something like 310. And if you draw this line, right, the vapor pressure of water is the lowest, something around 5, and then isopropanol, and then the vapor pressure of methanol is the highest. Because water has the lowest vapor pressure at any given temperature, water must have the strongest intermolecular forces, strongest attractive interactions. And because methanol has the highest vapor pressure at any given temperature, methanol must have the weakest intermolecular forces. So we know that that's all we need to solve this problem. Weakest must be methanol. This must be between B and C. And then greatest must be water, therefore option C. Okay, so let's pick option C. And moving on, question 6. All right, you are given a phase diagram. Select the paths that lead to changes in both average kinetic energy and potential energy. All right, so let's see, we have B to F. Okay, so here's B to F. You're going from lower temperature to higher temperature, therefore the kinetic energy increases. And then you are going from this is liquid to gas. Okay, and you can see that, and because you're lowering the pressure, okay, and increasing the temperature. So when this happens, the potential energy must increase, because you're going from liquid to gas. In liquid, you have particles closer to each other with stronger intermolecular forces, And in gas, we have weak intermolecular forces or weak attractive interactions. Therefore, potential energy must increase when you go from B to F. C to F. Let's see. Let's pick a different color. C to F. All right. The temperature is not changing. Okay. That means the kinetic energy is constant. If the temperature does not change, kinetic energy does not change. Okay. Because temperature is a measure of the average kinetic energy. If it doesn't change, the average kinetic energy stays the same. And then the potential energy must be increasing. Okay, potential energy must increase when you go from C to F. Reason is when you lower the pressure, the distance between the particles might increase over, okay? And as a result of that, intermolecular forces are weakened, therefore the pressure potential energy slightly increases. All right, let's move on to the next one. Let's pick a different color. Let's pick red. F2A is this, right? First of all, you're decreasing the temperature. That means kinetic energy decreases, okay? And then you are going from gas to solid. In the gases, we have the particles far apart from each other, weakest interactions, higher potential energy. And then in the solid, we have the particles closest to each other, and means strongest interactions, so strongest intermolecular forces, the lowest potential energy. Therefore, you are decreasing the potential energy. All right, so potential energy changes. So the question is, in which processes both kinetic energy and potential energy changes? That should be process 1 and process 3. 1 and 3, that's option B. All right, let's select option B. Moving on. Let's see. Okay, it's kind of difficult to get the entire picture, but anyway, the question is asking the wave pressure curves to methanol and all of them are given here. Select the correct pressure and temperature values for values that would correspond to the submicroscopic representation shown in the shown below. Okay, so here's a submicroscopic representation. You can see that isopropanol and methanol are here. Only isopropanol is in the liquid phase, methanol is in the gas phase. All right, so the idea is, if this is the situation, okay, so isopropanol is the gray curve, and then methanol is the blue curve. If isopropanol is in the liquid phase, that means you're above the curve of isopropanol, and then methanol is in the gas phase, that means you're below the curve of methanol. Therefore, you should be in this region, anywhere in this region. Okay. So let's see what conditions puts you there. Okay. So let's see. Okay, these are what we have. Let's say pressure 35 and 300K. 35K pressure, which is over here, and 300K temperature would put us at this point. Let's say A. Okay, and in this case, both species should be in the gas phase, because methanol, with respect to methanol and isopropanol, you are above the curve. That means you should be in the gas phase. Okay, so that is out. Okay, let's select, let's go with B, 25 and 300. 25 kilopascals and 300 should be over here. Okay, again, you're above both curves. You're above methanol, therefore methanol is in the liquid, phase here. Okay, so that doesn't work. Okay, methanol must be in the gas phase. If you're above the curve, you're in the liquid phase. All right, so moving on to C, 25 and 340. 25 is over here and 340 is over here. Okay, so this is our option C. In this case, you are below the curves of both methanol and isopropanol. Therefore, both of them are in the gas phase. Okay, that is out as well. We are not in this red region we have highlighted. That is out. So the correct answer must be option D, but let's see. 25 and 320. 25 kilopascals and 320 will put us over here. Okay, now we are above the curve of isopropanol, therefore isopropanol is in the liquid phase. We are below the curve of methanol, therefore methanol is in the gas phase. Therefore, that must be your answer, option D. Okay. Moving on. Which of the following graph represents the change in the potential energy of the particles in the system when the substances undergo the change corresponding to the path 2? Okay, so we're talking about path 2. We are going from gas to liquid. All right, and then we do that by decreasing the temperature. Therefore, we are cooling. Okay, and then if you look at the curve, then because we are cooling, and also when it comes to potential energy, we are always below zero because potential energy is always negative. Okay, and the highest is zero when the particles are far apart in the gas phase. But anyway, so we are going to go from a higher temperature to a lower temperature. Okay. See. All right, so here's the temperature. Okay, so we're starting from here. So let's say this is our T high, and we're going to end up over here. This is going to be T low. All right, so at high temperature, you should have potential energy closer to zero, high potential energy. Therefore, let's say that you are around here. Okay, this is my T high, and then when you decrease the temperature, the potential energy decreases slightly, and then during the phase transition, that is when it crosses the boundary over here. The temperature remains the same, but there will be a decrease in the potential energy. So let's call this the boiling temperature of the substance, or the condensing temperature of the substance. Okay, and then once everything is converted to liquid, then again when you change the temperature, change the potential changes slightly like this, and therefore this should be my T lowest. So again, whenever you are given a question like this, draw the graph first, and then look for your graph diagram in the given options. Okay, so I'm looking for this curve, and that looks like option D. So I'm going to select that, and then others are out. Okay, so option D is the correct answer. Let's see. All right, so the question is, based on the phase diagram below, select the changes in pressure or temperature that could lead to the process represented in this image. Okay, so take a screenshot again. All right, so you're going from nitrogen in the liquid phase to, nitrogen in the gas phase. Okay, right, nitrogen, here are my nitrogen in the gas phase, and now in after case you have all the nitrogen in the liquid phase. Okay, so you are condensing nitrogen. That is what is happening here. So that means you are going from blue region to yellow region. And then let's consider these processes. Pressure 1 bar, and then you are increasing that to 100 bar at 0 degrees. Okay, here's 1 bar, and then at 0 degrees, and then here's 100 bar. Yep, you went from gas to liquid. You went from blue region to yellow region, meaning you're going from this is liquid, this is gas. You're going from gas to liquid, so that works. Option A. All right, and then 2. At 100 bar, you're going from minus 25 degrees to 0 degrees. So you're going from here to here. No, this will be, I mean, you will stay in the liquid phase here. This happens. So that is not going to help. So that is out. Okay. And temperature at 10 bar, you're going from 0 to minus 50. Okay. At 10 bar, here's 0. Okay. And then here's minus 50. There you go. You're going from blue region to yellow region. So that works too. Options 1 and 3 should be your answers. 1 and 3 are the correct answers. Okay, let's tackle this problem. Based on the image above, representing a mixture at 298 Kelvin, select which statements are consistent with the particulate model of matter. Okay, now 298 Kelvin, that means all of them have the same average kinetic energy. So that is true. The number 1 is correct. Okay, temperature is a measure of the average kinetic energy. Because they are the same temperature, they should all have the same average kinetic energy. And then nitrogen molecules have the highest average potential energy. You can see that nitrogen molecules are in the gas phase, meaning you have the weakest attractive interactions. Therefore, we should have the highest potential energy. Therefore, that is correct too. And option 3 is H2O molecules are moving at the lowest average speed. Now, H2O molecules and all the other molecules have the same average kinetic energy. Okay, but the thing is, H2O it's around 18 grams per mole, and then C2Cl4 is much heavier than that. Okay, C2 is 2 times carbon, that means 24, plus Cl is 35.5. You have 4 of them, so it's just like, I don't know, 100 okay, give me a second. 35.5 times 2 is 71. 71 times 2 is 142. 142 plus 24 is 166 or something like that. It's very heavy. Okay, so C2Cl4 is the heaviest. Therefore, C2Cl4 must be moving the slowest out of all of these particles. Okay, if they have the same energy, the particle with the highest mass should be moving the slowest. It's like this. If the Tesla car and an 18-wheeler had the same energy, then the Tesla car, which is much lighter, should be moving the fastest. Okay, so just like that, when the particle is heavier compared to a different particle, that particle must be moving slower. Okay, and then on the other hand, if the particle is lighter, it must be moving faster to compensate for the lack of the mass, because kinetic energy is half mv squared. Anyway, so the option 3 is incorrect. Option 1 and 2 are correct. I would select option A. Okay, lowest average speed must be in C2Cl4, not H2O. All right, moving on. Here's a numerical question. You have a balloon. You have the initial volume V1. This is T1, and this is P1. And then what we know that PV is equal to NKBT, and then PV over T is NKB. Because we are not changing the number of particles, which is N, and the Boltzmann constants case are B. Okay, this thing is constant. Okay, therefore we can say that P1 V1 over T1 is equal to P2 V2 over T2. Okay, now we are told that temperature is increased by 4 times. That tells me that P1 V1 over T1 must be equal to temperature is 4 times the initial temperature. Temperature is increased to 4 times its initial value, 4 times T1. And then the pressure is also increased to 2 times its initial value. So P2 must be 2 times P1. And they're asking for the volume, the final volume V2. Okay, so what we can do is we can cancel out P1 with P1, T1 with T1, and then we can rewrite this saying V1 is equal to 2 times V2 divided by 4. Therefore, V2 is equal to 4 times V1 divided by 2, which is 2 times V1. All right, now we know V1 is 20 liters. Therefore, 2 times 20 liters is 40. With a decimal point, okay, let's see, 40 liters, that should be your answer. Okay, so let's enter that. We can enter 40, 0. That's our answer without the units. Okay, so in this problem, you are given A and B. You need to put that on a peg diagram. Okay, now B definitely has a higher number of configurations. Okay, therefore option D is out, because in option D, A has a high number of configuration. And also option B is out, because in option B, you have A has a higher number of configuration. So that is out. And also there is number of configuration. When it comes to potential energy, it's all about the strength of interactions between the particles. And we have the particles closer to each other in A compared to B on average, meaning in A, we should have stronger intermolecular forces or stronger attractive interactions. Therefore, A should have a lower potential energy. Okay, between A and C, only A, option A has a lower potential energy in A. Therefore, that must be the correct answer, option A. Okay, moving on. Okay, in the peg diagram. Okay, and the question is asking which of the following statements is true. You have two statements. Let's read one statement to know what they're referring to. Particles in the mixed state have weaker interactions, so they're talking about the interaction strength. An increase in the temperature should favor the formation of the mixed state. Okay, so the strength of interactions and then how the temperature affect the states. Okay, that's the question here. Now here's the thing. We have a lower potential energy in the unmixed state. Therefore, you should have stronger IMFs here, and then weaker interactions, weaker IMFs in the mixed state. Okay, that's the first thing. The mixed state have weaker interactions is correct. Okay, whatever the statement saying mixed state has weaker interactions is correct, because higher potential energy means weaker interactions. Okay, so option A is fine for the moment. Mixed state has stronger. This is wrong. Mixed state should not have strong interactions. And C, particles in the mixed state have weak interactions. Okay, that is fine. Since have weak interactions. And option D, particles in the mixed state have strong interactions. Okay, this is incorrect. So that is out. Okay, now we have determined the interaction strengths part. The other part is the effect of temperature. High temperatures favor the state with high potential energy. Okay, the reason is if you have a high temperature, that means you have a higher kinetic energy. That means particles are moving fast. And then when the particles are moving fast, you cannot have stronger interactions between the particles. Therefore, that is going to favor weaker interactions. That means a state with high potential energy. That's the idea. Anyway, so therefore, increase in temperature should favor the mixing or the mixed state. And option A says particles in the mixed state have weak interactions, which is correct, and increase in the temperature should favor the formation of the mixed state. That is absolutely correct. Okay, and let's read option C as well, even though we already have the answer. Particles in the mixed state have weak interactions. That is correct. And decrease in the temperature should favor the formation of the mixed state. That is incorrect. Okay, high temperatures favor the high potential energy state. So therefore, mixed state will be favored at high temperatures, not low temperatures. Option A is the correct answer. Okay, moving on. How many chemical compounds are represented in this mixture? Chemical compounds contains 2 or more types of atoms. Okay, and then we have CH4 with carbon and hydrogen. Then we have at the bottom we have the liquid HCN with different atoms, so that should be 2. Okay, so let's see. Okay, question 15. Write the mass of samples of CBr3 and these substances. Anyway, now here's the thing. It doesn't matter whether we had 1 particle or 3.2 times 10 to the power of 22 particles. Okay, whatever the substance which has a higher relative atomic mass, relative molecular mass, or relatively higher molar mass, should have the highest mass. That is it. Okay, so it's all about the mass. It's not talking about the number of particles. Doesn't matter. Anyway, so carbon is, let's think about CBrF3, and it should be 12 plus 80 plus fluorine is 19. 19 times 3 is 57. 57. This is like let's say 80, 92, 92, and okay, so 92 plus 57 is 149, right? Let me check that. Okay, so we have 12 plus 80 plus 57 is 149. Yeah, 149. And then we have CHFCl2. Carbon is 12. Fluorine is 19. Chlorine is 35.5. You have 2 of them, that is 71. So 71, 91, 90, 102. This should be 102. And then we have CF3Cl, that is 12 plus 3 times 19 is 57 plus 35.5, and that's going to add up to 57, 87, 87, 92.5. 92.5 plus 12 is 104.5. Okay, so the heaviest is CBrF3. Highest mass is, oh, there's only one answer with that, CBrF3, and then CF3Cl, and the lowest mass is CHFCl2. The correct answer is option C. Okay, let's go with option C. Moving on to question 16. In the mixture of substance shown below, rank the particles from lowest to highest average speed at 300 Kelvin. Okay, so this is again about the molar mass. Okay, the heavier particles will be moving the slowest or the lowest average speed, and then highest heaviest particles will have the heaviest particles will have the lowest average speed, and then lightest particles will have the highest speed. Okay, now anyway, we have hydrogen. These guys are the will have a molar mass of 2 grams per mole, or 2 AMU relative mass, so that this should be the fastest. And then we have let's say a CH4. Okay, they have a mass of 16, and then we have, let's say HCN. Okay, nitrogen is 14, carbon is 12, 26 plus 27, 27. And then we have nitrogens. Nitrogen one atom is 14, 14 times 2 is 28. That should be the heaviest. So the lightest is hydrogen, therefore it should be the fastest. It's like our car, Tesla car. And then nitrogen in 2 on the other hand is the 18-wheeler, heaviest. That should be moving the slowest. Okay, now let's see. Lowest to highest average speed. Highest must be hydrogen. So it's between the first one and the second one. And the lowest must be nitrogen. That is option D. Okay, so let's pick that answer. Moving on, the last question. All right, you are given a molecule, you asked to find the molar mass of the compound. So let's do that. The black atoms are carbons. We have 1, 2, 3, 4, 5. C5, carbon 5. And then hydrogens are the white ones, white small ones. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 hydrogens. And the blue one should be nitrogen. We have 1 and 2 nitrogens. Okay, so if we add them up, 5 times 12 plus 14 times 1 hydrogen, and then 2 times 14 for nitrogens. Okay, so 5 times 12 is 60. 14 times 1 is 14, and 2 times 14 is 28. So if you add these up, it should be 88. 88, 98 plus 4 is 102. So 102 is over here. That should be our answer. 102. That's it. And let's submit our quiz. Okay, and here we go. Fine. Okay. Things seems fine. Okay. Yep, we got 100%. All right, I hope this helped. I'll see you guys in class. Bye, everybody.